One of the most intriguing questions humans have grappled with is whether we are alone in the universe. However, the James Webb Space Telescope threatens to complicate the quest even further with its recent discovery of a universe that existed before ours. What is this universe? Where did it come from? And does it have any effect on our own universe? Join us as we dive deep into how the JWST detected a universe that existed before ours. The JWST is the most powerful astronomical instrument ever created. This Hubble successor is intended to observe the universe in a variety of wavelengths, from visible to infrared, allowing us to see objects and events that were previously invisible to us. The JWST, with its advanced technology and incredible capabilities, is poised to solve many of the universe's mysteries, including the cosmos's early history. Our knowledge of physics is insufficient to explain the early universe. The JWST's ability to look back in time and see the universe as it was in its early days is one of its most exciting prospects. Light from distant galaxies takes billions of years to reach us, so when we look at distant galaxies, we see them as they were billions of years ago. And we can observe these galaxies in detail thanks to the JWST's incredible sensitivity and resolution, allowing us to understand how they formed and evolved over time. Observing the first galaxies that formed after the Big Bang is one of the key ways that the JWST can help us understand the early history of the universe. These galaxies, which are extremely faint and distant, are thought to have formed only a few 100 million years after the universe began. The JWST's infrared capabilities enable it to detect the faint light emitted by these galaxies, which has been redshifted due to the universe's expansion. We can learn about the conditions that led to the formation of these early galaxies, as well as the evolution of the universe in its early days, by studying these early galaxies. The JWST can also help us understand the early universe by studying the first stars to form. These stars are thought to have formed within the first few 100 million years after the Big Bang and were very different from the stars we see today. They were almost certainly much larger and hotter, and they could have had a significant impact on the evolution of the universe. And because of its ability to detect faint infrared emissions, the JWST is ideal for studying these early stars. The JWST can also help us understand how galaxies form and evolve over time. We can see how distant galaxies formed and evolved over time by observing them in the early universe. We can also study galaxies' interactions to better understand how they merge and form larger structures. And we can learn about the large-scale structure of the universe and how it has evolved over billions of years by studying the distribution of galaxies over time. Now, deep-field images obtained by the JWST during its early observation campaign appear to be full of galaxies nearly as massive as the Milky Way and full of mature red stars, giving astronomers a headache. These galaxies, described in a new study based on JWST's first data release, are so far away that the powerful telescope only sees them as tiny reddish dots. Astronomers determined that they were viewing these galaxies in the early stages of our universe, only 500 to 700 million years after the Big Bang, by analyzing the light emitted by them. Now, such early galaxies are not surprising in and of themselves. Astronomers predicted that the first star clusters would form soon after the universe emerged from its so-called dark ages, the first 400 million years of existence when space was filled with a thick fog of hydrogen atoms. However, the galaxies found in the JWST images were shockingly large, and the stars in them were far too old. The new findings contradict existing theories about how the universe appeared and evolved in its early years, and they contradict previous observations made by the JWST's less powerful predecessor, the Hubble Space Telescope. Scientists had specific expectations for the type of galaxies that live in the early universe. They are young and small, according to Joe Leyer, assistant professor of astronomy and astrophysics at Penn State and one of the study's authors. Previous Hubble and other instrument studies of the early universe have found small blue baby galaxies at early times, objects that have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. In general, young stars shine a bright blue. As stars age, their glow becomes redder as they burn through their fuel and cool. Astronomers had not expected to see old red stars in the ancient galaxies that JWST was designed to observe. They also did not expect to find galaxies larger than 1 billion suns. However, the reddish dots revealed in JWST's deep fields appear 50 times larger. But before astronomers start rewriting cosmology theories to explain how these galaxies came together so quickly after the Big Bang, Leyer says they need to make sure the strange red dots they're seeing aren't something else. The majority of the alternative explanations, however, require entirely new concepts. For example, stars in the early universe may emit light in unusual ways due to a lack of heavy elements, which may not be accounted for in our models. Alternatively, perhaps our understanding of how stars form locally, such as how many stars form from gas as a function of star mass, is completely irrelevant in the early universe. These discoveries would be exciting and would challenge our understanding of star formation in the early universe, albeit in a very different way. Webb's near-infrared camera captured the images that revealed these perplexing galaxies as part of the Cosmic Evolution Early Release Science, or SEERS program. JWST unleashed a torrent of discoveries in the summer of 2022. JWST was fully operational in July 2022 following a December 2021 launch and more than a year of commissioning. Almost immediately after that, its unprecedented infrared sensitivity revealed faint glows of galaxies that appeared to be from a distant universe that had formed only hundreds of millions of years after the Big Bang. Astronomers expected such historic results to emerge gradually, but what they got was an explosion of data. Researchers were able to produce those early results so quickly because they used a clever shortcut to estimate galactic distances. Astronomers typically determine cosmic coordinates by precisely measuring redshift, the stretching of a galaxy's light towards the red end of the electromagnetic spectrum caused by the expansion of the universe. However, this necessitates the assembly and analysis of a galaxy's spectrum, a time-consuming and subtle process known as spectroscopy. JWST's Discovery Firehose was instead powered by cruder, faster photometry-based techniques that essentially use obvious variations in the brightness of galaxies to estimate their redshift. As a result, while photometric results came thick and fast last summer, spectroscopic results have only recently begun to trickle in. However, so far, with only about a dozen candidate spectra-based distances in hand, researchers are finding that most measurements match the early photometric results. The most recent results confirm earlier distance estimates for 4 more galaxies discovered by the JWST Advanced Deep Extragalactic Survey, JADES. Scientists have been waiting decades for this, so to be able to do it within the first few months of using this telescope was just incredible. The most distant of the 4 is the one with the somewhat unwieldy name JADES GS-Z130. It has a redshift of 13.2, indicating that we are viewing the galaxy as it appeared 320 million years after the Big Bang. Because of the high redshift, JADES GS-Z130 is the most distant object currently known in the universe. a record that JWST appears set to break soon, but one that demonstrates why astronomers are so excited. We now know for certain that we are exploring an era of the universe that no human has ever seen before. This galaxy is only slightly older than the total time sharks have existed on Earth, roughly 300 million years. You go from nothing to these fully formed galaxies in the blink of a galactic eye. However, not all high redshift candidate galaxies have been so fortunate, highlighting astronomers' early caution. The Sears survey discovered a possible galaxy at a redshift of 16.4, just 240 million years after the Big Bang. However, subsequent spectroscopy revealed that the deduction was incorrect. The galaxy is actually a dusty imposter located at a redshift of 4.9, 1.2 billion years after the Big Bang, which is still impressive but not unprecedented. Early photometric analysis is thought to have been muddled by high levels of star formation. Researchers can be easily fooled by contamination. A high redshift galaxy can be mimicked by a lower redshift galaxy with different features. The good news is, though, that this galaxy appears to be a unique case. The same study confirmed that two other candidate galaxies did not have the same issue. One of these is Mais's galaxy, which was named after one of the researchers' daughters and can be seen at a redshift of 11.4, about 400 million years after the Big Bang. Now that such galaxies have been confirmed, their scientific implications can be investigated further. These galaxies are extremely small, many times smaller than the Milky Way. However, some appear extremely bright and massive, with star formation rates comparable to our galaxy, which forms about one new star every year. While the galaxies do not yet challenge leading cosmological models, they do suggest that galactic formation began earlier and proceeded faster than expected in the universe, which theorists previously predicted would begin producing galaxies 1 billion years after the Big Bang. What we see here is a faster rise of massive galaxies than we previously thought. Some of these early galaxies are estimated to be tens of millions of years old. This could have implications for the nature of dark matter particles, as well as the large structures of dark matter known as halos that sculpted early galaxies. But one of the big open questions is, what is dark matter? Well, the first generation of galaxies are a sensitive probe for different dark matter models. Some problematic and potentially model-busting candidate galaxies from the early universe remain. The first could be a class of galaxies discovered by Ivo Labbé of Australia's Swinburne University of Technology and his colleagues. The team discovered galaxies with billions of solar masses comparable in mass to the Milky Way only 750 million years after the Big Bang. These galaxies are 10 to 100 times larger than previous galaxies seen in this era, and they are packed into structures 30 times smaller than the Milky Way. They're small, but they're massive, says Labbé, who adds that the JWST is still discovering similar galaxies almost anywhere it looks deeply into the sky. Now, for the time being, the galaxies have only been studied through photometry, with spectroscopic analysis scheduled for July. However, the photometric success of previous JWST results suggests that Labbé and his colleagues' preliminary analysis is correct. The most extreme galaxies there still seem to pose a problem, says Michael Boylan-Colchin of the University of Texas at Austin, who was not involved in the JWST observations discussed here. Some of these systems must be forming stars 1,000 times faster than the Milky Way. The question is that an unfathomably high rate of star formation? The field is changing at a rapid pace. A current survey known as Cosmos Webb is expected to yield many more high redshift candidates. The estimates in the proposal were to find galaxies up to a redshift of 10 or so. However, those figures could have been overly pessimistic. Many other astronomers have asked the Space Telescope Science Institute in Maryland, which operates the observatory, for more spare time on the telescope. More proposals have been received for the telescope's second year of scheduled scientific observations, known as Cycle 2, which begins in July. However, some are concerned that the pitch is moving too quickly. While approximately 80% of JWST data has a proprietary window of 12 months, during which the researchers responsible have exclusive access to their own observations, the remainder is open access. This means that when observations are made, they are immediately available to the public and can be used by anyone. One of the things the JWST will help scientists do is test various theories about the state of the universe at the initial stage. One of these theories is that there was a universe existing before this one. Now, so far we do in fact have a fairly detailed understanding of how the first atoms formed from simpler particles once conditions cooled sufficiently to allow complex matter to be stable, and how these atoms were later fused into heavier elements inside stars. However, this comprehension does not address the question of whether something came from nothing. So let's go back further. Protons and neutrons, which make up the atomic nucleus, were the first long-lived matter particles of any kind. These appeared approximately 1/10,000th of a second after the Big Bang. There was no material in any conventional sense prior to that point. However, physics allows us to continue tracing the timeline backwards to physical processes that predate any stable matter. This brings us to the Grand Unified Epoch. We've entered the realm of speculative physics by now, as we can't generate enough energy in our experiments to probe the kinds of processes that were going on at that time. However, one plausible theory is that the physical world was made up of a soup of short-lived elementary particles such as quarks, the building blocks of protons and neutrons. Matter and antimatter were present in roughly equal quantities. Each particle, such as the quark, had an antimatter mirror image companion that is nearly identical to itself and differs only in one aspect. When matter and antimatter collide, they annihilate in a flash of energy, implying that these particles were constantly created and destroyed. But how did these particles form in the first place? According to quantum field theory, even a vacuum, which is supposed to correspond to empty space-time, is full of physical activity in the form of energy fluctuations. These fluctuations can cause particles to emerge only to vanish shortly afterward. This may appear to be a mathematical quirk rather than actual physics, but such particles have been observed in numerous experiments. The space-time vacuum state is rife with particles that are constantly being created and destroyed, seemingly from nothing. But perhaps all this really tells us is that, contrary to its name, the quantum vacuum is a something rather than a nothing. The philosopher David Albert famously criticized Big Bang theories that promise to create something out of nothing. So let us speculate. Where did space-time come from? Then we can go even further back in time to the truly ancient Planck epoch, a period so early in the history of the universe that our best physics theories fail. This era occurred only 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the Big Bang. Space and time themselves become subject to quantum fluctuations at this point. Now, physicists typically work with quantum mechanics, which governs the micro-world of particles, and general relativity, which governs large cosmic scales. To truly understand the Planck epoch, however, we need a complete theory of quantum gravity that combines the two. Now, there is no perfect theory of quantum gravity, but there are attempts such as string theory and loop quantum gravity. Ordinary space and time are typically seen as emergent in these attempts, much like the waves on the surface of a deep ocean. What we perceive as space and time is the result of quantum processes at a deeper, microscopic level, processes that make little sense to us creatures rooted in the macroscopic world. Because our ordinary understanding of space and time fails in the Planck epoch, we can no longer rely on our ordinary understanding of cause and effect. Regardless, all candidate quantum gravity theories describe something physical that occurred during the Planck epoch, some quantum precursor of ordinary space and time. But how did that happen? Well, even if ordinary causality no longer applies, it may still be possible to explain one component of the Planck epoch universe in terms of another. Unfortunately, even our best physics no longer provides complete answers. We won't be able to provide a definitive answer until we make further progress toward a theory of everything. At this point, the most we can say with certainty is that physics has found no confirmed instances of something arising from nothing. To truly understand how something could emerge from nothing, we would need to explain the quantum state of the entire universe at the start of the Planck epoch. All attempts to do so remain speculative. Some of them, like a designer, appeal to supernatural forces. However, other candidate explanations remain within the realm of physics, such as a multiverse which contains an infinite number of parallel universes or cyclical models of the universe in which the universe is born and reborn. The Nobel Prize-winning physicist Roger Penrose proposed an intriguing but controversial model for a cyclical universe called conformal cyclic cosmology in 2020. Penrose was inspired by an intriguing mathematical connection between a very hot, dense, small state of the universe at the Big Bang and an extremely cold, empty, expanded state of the universe in the far future. His radical theory for explaining this correspondence is that when those states are stretched to their limits, they become mathematically identical. Even though it may appear paradoxical, a total lack of matter may have managed to give rise to all of the matter we see around us in our universe. According to this theory, the Big Bang arose from almost nothing. That's what remains after all of the matter in the universe has been consumed by black holes, which have then boiled away into photons lost in space. Thus, the entire universe emerges from something that, from another physical standpoint, is as close to nothing as one can get. However, that nothing is still something. It is still a physical universe, albeit an empty one. But how can the same state be seen as a cold, empty universe from one angle and a hot, dense universe from another? The solution lies in a complex mathematical procedure known as conformal rescaling, a geometrical transformation that changes the size of an object while leaving its shape unchanged. Penrose demonstrated how such rescaling could link the cold, empty state and the hot, dense state so that they match in terms of the shapes of their space-times but not in terms of their sizes. It is difficult to understand how two objects with different sizes can be identified in this way, but Penrose argues that size as a concept ceases to make sense in such extreme physical environments. The direction of explanation in conformal cyclic cosmology is from old and cold to young and hot. The hot, dense state exists because of the cold, empty state, but this because is not the familiar one of a cause followed by its effect over time. In these extreme states, not only size but also time ceases to be relevant. In practice, the cold, dense state and the hot, dense state exist on different timelines. From the perspective of an observer, the cold, empty state would last forever in its own temporal geometry, but the hot, dense state it gives rise to effectively inhabits a new timeline all on its own. It may help to understand the hot, dense state as a non-causal result of the cold, empty state. Perhaps the hot, dense state emerges from, is grounded in, or is realized by the cold, empty state. These are distinctively metaphysical ideas that have been extensively investigated by philosophers of science, particularly in the context of quantum gravity, where ordinary cause and effect appear to break down. Physics and philosophy become difficult to separate at the limits of our understanding. Conformal cyclic cosmology provides some detailed, albeit speculative, answers to where our Big Bang originated. But even if Penrose's vision is vindicated by future advances in cosmology, we may conclude that we still haven't answered a deeper philosophical question: the origin of physical reality itself. How did the entire cycle system come to be? Each with its own universe, with the initial quantum state of each universe explained by some feature of the universe before. Or there could be only one cycle and one universe, with the beginning of that cycle explained by some feature of its own end. The latter two approaches do not require any uncaused events, which gives them a distinct appeal. Physics would leave nothing unexplained. Now, Penrose envisions an infinite number of new cycles for reasons related to his preferred interpretation of the quantum theory. A physical system exists in a superposition of many different states at the same time in quantum mechanics, and only picks one randomly when we measure it. According to Penrose, each cycle involves random quantum events that result in a different outcome, which means that each cycle is distinct from those before and after it. And this is actually good news for experimental physicists, because it may allow us to see the old universe that gave birth to ours by detecting faint traces or anomalies in the leftover radiation from the Big Bang detected by the Planck satellite. Penrose and his colleagues believe they may have already discovered these traces, attributing patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, other physicists have challenged their claimed observations, and the jury is still out. Endless new cycles are essential to Penrose's vision. There is, however, a natural way to transform conformal cyclic cosmology from a multi-cycle to a one-cycle form. Then physical reality is a single cycle around the Big Bang to a maximally empty state in the far future, and then back around to the same Big Bang, giving rise to the same universe all over again. This latter possibility is consistent with another quantum mechanics interpretation known as the many worlds interpretation. According to the many worlds interpretation, when we measure a system in superposition, we do not choose a state at random. Instead, the measurement result we see is just one of many possible outcomes, the one that occurs in our own universe. The other measurement outcomes all take place in other universes, in a multiverse that are effectively cut off from our own. So no matter how remote the possibility of something happening is, if it has a non-zero chance of happening, it will happen in some quantum parallel world. There are people out there in other worlds who have won the lottery, been swept up into the clouds by a freak typhoon, spontaneously ignited, or done all three at the same time as you. And some believe parallel universes can be seen in cosmological data as imprints left by another universe colliding with ours. The many worlds quantum theory adds a new twist to conformal cyclic cosmology, but not one with which Penrose agrees. Our Big Bang could be the rebirth of a single quantum multiverse containing an infinite number of different universes, all happening at the same time.